I'm going to talk about 2D materials and electronics, and this is not something I've talked about too much with this group, but it's what I've done for a long time, nanomaterials and electronics. And you'll see that it's been an interesting journey, and I think that there's a few of us that have learned a lot along the way and are forming something of an industrial nanotechnology community, which is a little bit separate, but definitely connected to the academic nanotechnology community. So in the mapped roadmap, and I want to emphasize that this is overall very good. The mapped roadmap lays out the role of 2D materials in the future of electronics. This is just some of the highlights here. So, you know, that low dimensional materials are promising candidates for extremely scaled devices. When we get to hyperscaling, when we get to the, you know, the so-called one angstrom, sorry, 1 nanometer node, you know, this is where we're seeing 2D materials or carbon nanotubes kind of find their way into the roadmap in a practical way. It's also promising for low power applications, and that's definitely one of the driving factors for why I think 2D materials apply to the future of electronics. The mapped roadmap calls out Skywater and ADI as places that are working on integrating CNTs and graphene into the fab. Again, kind of that proof point that someone out there in industry is trying to make these things work is really helpful. Because for a very long time, the story was that no one was really trying to make it work commercially. And then there are some challenges listed out. Material growth and deposition was really highlighted a few times in the roadmap. And then other issues that were listed out were improved materials for ohmic contacts and improved materials for gate insulator integration. And the words in the roadmap may be a little bit different, but those are kind of the take-home messages. And then the pathway forward is focus on improved growth and deposition, find some better etching techniques. These are different materials than we're used to using. Find better deposition of materials, ways of depositing materials on top of low dimensional materials. So the chemistry is different. So I'm going to go into a deep dive on some of these things, and then a point of view on that's a little bit different from what's in the mapped roadmap right now in terms of what I think we should be focusing on. A lot of the technical details are right, but there's some emphasis that I would do a little bit differently. And in order to do that, I want to back all the way up to something that might be familiar to Victor, or definitely is familiar to Victor. So I think that graph on the left, I don't know if you made it, Victor, but that's from the National Nanotechnology Roadmap. And for a few of us, this was kind of the roadmap that led us through the beginning parts of our careers. There's several of us out there. I'm joined by Ramon from SRC today, and myself, that kind of got our start in the early 2000s, looking at the NNI roadmap and kind of thinking about how this was going to work, how we were going to get our research at that point integrated into electronics. And you can see from 2000 to 2009, 2010, there was a steady increase in funding for nanotechnology, including nanoelectronics, year over year. It was this really rapid boom cycle. It was very exciting, and a lot of optimism. And then around 2010, the funding drifted off, and the thought, I think, at the time was that more private entities would pick up the funding. However, there was also a contraction in the VC market at that point, and so the overall funding for nanoelectronics decreased. And it led to a lot of feelings of disappointment and frustration in the field, because over that course of 2000 to 2010, I would say we did a relatively poor job of trying to figure out how to integrate carbon nanotubes into conventional electronics. We focused a lot on publishing papers and getting PhDs minted, and we did a very good job of that. I think on my next slide I talked about that a little bit, right? And really, it's not like we were horrible people or anything, right? This is a normal part of a new technology hype cycle. So amongst the thought leaders in nanotechnology at the time, there were relatively few people who had commercial experience. and there were relatively few people who were really pushing for the kinds of things that need to be done in order to make a practical technology. We didn't focus on integration. It was very rare in those first 10 years for people to work on completely packaged chips, which meant that all the difficulties that come with packaging were just completely ignored. I mean, I remember some conversations I had with people about wire bonding and epoxy that were really eye-opening in the early 2010s. It was rare for us to cross-train into CMOS and 3.5 technologies, right? We were very focused on our nanomaterials. There was not really a discussion of yield, right? There were a lot of hero device stuff, and we had this very competitive culture that led to over-specialization. So there was not a good appreciation of all the different things that needed to happen in order to make a practical device. And again, I'm not saying we were horrible people. It's just kind of the way things happen in the early stages of technology development. But I think the biggest problems was that we didn't have an incentive to do better. So the grant funding was very plentiful and ever increasing over that period of time. There wasn't pressure on us to actually, move things off into industry, at least on an individual level. During those early years, VCs were happy to provide investment just based on the excitement. And there were a lot of people, particularly there was the, I would say the leading industry lab at the time was at IBM. And they were happy, to just get good marketing material. And I say just, it was extraordinarily good marketing material. They were really thought leaders in the world of nanoelectronics. And, highlighted at every conference. It was really quite good for them. And, in the defense of me and people my age, right, much of the science that we did was really very good. So we did a lot of really good things in those early years that we continue to keep mining as we go further into commercialization. But what I'm going to try and talk about today is as we get into this next stage where nanoelectronics is once again kind of on a roadmap, what do we have to do to make sure that we don't repeat the past mistakes and we keep a focus on some of the practical aspects of technology development and don't get overexcited by a couple of kind of promising hero devices, but instead get excited by things like yield and performance apples to apples with existing electronics. So something that I don't know how many people are kind of familiar with the current landscape of nanomaterials out there. Broadly speaking, we are also talking about carbon nanotubes, but generally we're talking about two-dimensional materials like graphene, which I would argue graphene itself does not play such a huge role in the future of electronics, although it's the current commercial 2D material. Really, the future is going to be these other materials, things like black phosphorus or phosphorine, hexagonal boron nitride, and then these transition metal dichalcogenides, and then other types of MXenes that are related to these TMDs. These materials are, semiconductors, so they're a little bit easier to work with in terms of making actual devices compared to graphene. But graphene is the one that we know how to work with the best today. I would say, Ramon, one of the reasons I asked you if you could join is you have more of a feel for kind of what's going on in the research world than I do. And at any time, if you kind of thought, hey, you're missing a couple things, just please speak up and let me know. You were also there in those early years.
Yeah, thanks, Brett. Some thoughts that even just crossed my mind in seeing the fall off in funding on that first slide that you showed. One additional point to the ones you mentioned is the discovery of graphene happened shortly before that fall off in funding in carbon nanotubes. And that's reflected in that as the excitement kind of shifted from carbon nanotubes, which were very promising with device properties, but extremely difficult to integrate because of alignment and purification challenges, et cetera. And all of a sudden you had these new 2D materials come onto the scene that people could see a path forward to integrate them. But, for electronics, as you pointed out, graphene doesn't have a band gap. So it took a while before the TMDs then came along and we were able to apply some of the knowledge we learned from graphene to these two-dimensional materials with a band gap. And that's kind of where we still are at today, right? There's many challenges to remain. So yeah, just thank you for inviting me, and it's nice to see the progress.
Yeah, thanks. That's a really good point. I think that the excitement around graphene really did shift the field and established what could have become a really unfortunate pattern of repeating the same basic research over and over again on different materials. And for a while, it looked like that's where we were headed. But I think with the TMDs and the focus that we're getting from commercial organizations now to work hard on integrating these materials into practical devices, I think we're going to be able to break out of that idea that, hey, we just need to wait for the next new material. But let's actually try and get some of these ones that we have on hand now to work. So some of the challenges with these types of materials, these TMDs and these graphene-like materials, right? They really can't be grown in place on CMOS wafers. And a lot of this, I'm throwing yets and things like that in there, right? So we can't yet really do direct integration with CMOS or really any sort of conventional semiconductor in terms of grown in place. There's other ways you can do integration, but that becomes challenging because you're talking about doing essentially brand new processes that aren't familiar in a fab. The electrical contact should ideally be made by a semi-metal like tin or bismuth, and this is pretty exotic. And so, figuring out how to make a good contact that's reliable and high performance is really a challenge. It might require new materials. To me, this next one is probably the biggest issue. It's one I've struggled with over the last 15 years of working on this commercially. This growth of oxides via ALD or plasma deposition on these materials is very difficult. And I don't think it's really suitable to count on using these techniques in the long term. My personal view is I just don't think you're ever going to get yield unless we start thinking about different ways of doing dielectric deposition. Etching these materials is difficult, right? So they're not conventional. It's not silicon. It's, we've got to figure out different etch techniques, things that are specific to these materials, and certainly people are working on it, but it's change, right? You're using different gases, you're using different processes, different temperatures. It's easy to damage these materials during handling. One of the things that I think got oversold about nanomaterials is how strong they are, right? Stronger than steel. Well, if you had a layer of steel that was the same thickness as graphene, it would spontaneously combust in air. So the bar is the materials don't spontaneously combust in air. All right, good. We've got that, but they're really, if you mechanically touch them, you can damage them very easily. And if you really want to send a nanoelectronics person into conniption fits, just ask them to do a scratch test on their wafers, and I've never seen a wafer that will pass a scratch test that had a 2D material layer on it. It just won't do it yet. And of course, we don't know which material is best yet for digital circuits. There's a lot of conversations about kind of which of these TMDs is best, and depending on who you ask, you're going to see different points of view, and that's just, I think, where we are. But that might change quickly depending on how the JUMP program goes and things like that. So, why do we care at all? Because we had these bullet points from before saying that we think it's the future and might have some contributions to power and things like that. So this is from last year from the Intel group that focuses on 2D materials, and it's a pretty crunchy paper communication on why they care about 2D materials, what they expect these types of materials to provide. And so they did initially some simulations showing that the 2D nanosheets should get us better performance in terms of sub-threshold swing as we get to smaller sizes. And so it's kind of, we need to maintain the 70 millivolts per decade sub-threshold swing. The gate length over time is going to get down low. So this is about really small gate length. So this is not next year or the year after. This is down the line. As we shrink the gate length, the channel thickness needs to get below 5 nanometers to maintain all of these things. And at that point, you get a lot of tunneling current. through silicon and your off state current is just too high, you're going to just burn a lot of energy. And so 2D materials avoid this and provide you with advantages. So the neat thing here is that they've built some of the structures that they're talking about, and other people have too, but I like this because it's nice and encapsulated and you can see what they've done. And so they've got one of their TMDs here. If you can see that, but with this gate all around structure and a gate oxide, and this is a really hard thing to manufacture, but they've managed to manufacture a bunch of them, and they can demonstrate they can make these structures. So that's very cool. And I particularly like that this is an industry group doing this, and it shows that we're developing in our field some expertise within commercial organizations of how to use these materials and really starting to think about how to practically integrate them with the types of chips that we know how to make in industry. I prefer this graph, really. I'm a physicist, and so this graph, to me, it's a little bit harder to decode, but it tells me why we care. So let's see if I can, well, the orange here, that's silicon. And I'm not sure I like the labels of 2019 and 2028, but this is basically showing what I've been talking about, going from current fab to 10 years from now fab approaches and how we expect the scaling to work. And this is an older paper. It's from 2016, not last year, but this is all modeling, and it shows essentially the power use in a transistor made from different materials with the same design. So if we had the same geometry, what would the power use for a transistor be using these different things? So the kind of diagonal lines are lines of uniform power per switching, and they go. You can see that from the orange silicon points down to the TMDs and these other materials, you're getting lower power per switching for the same design, and it's not, a little bit, it can be very significant. And so when I see the types of plots that we've been generating here with the mapped team over the last good while, looking at the need to decrease the energy use in electronics, I'm excited that the 2D materials might play a role in that in the kind of 10-year time frame. So I work for Paragraph, so I'm gonna talk about Paragraph a little bit. I think it's useful to have some proof points. So I talked about Intel, and there's a couple of other companies out there, but one of the things I wanted to mention is that there are commercial teams working on integration of these materials. And today, it would be pretty ridiculous to try and make commercial digital electronics with 2D materials, but we can make other types of devices. And as we work on getting those types of devices through the fab, we're learning a lot about integration, right? We still have to worry about contact metals. We still have to worry about how we do dielectrics. We still have to worry about packaging and yield and all these things, even though the performance bar is way, way lower for the types of devices that we're making. So Paragraph is an interesting company. It was founded by people who came from the 3.5 industry. So essentially, I'm a nanotechnologist. I've never made CMOS chip in my life. 3.5 chip, never done that. Just worked on nanomaterials. I'm the only person like that at the company. So everyone else is conventional electronics person. So that's kind of an interesting position for me to be in. But it means that the way the fabs are built, the way the processes are developed, it's 3.5. We're following conventional 3.5 designs and processes and workflows as much as possible. Now it's a UK company. In the UK, there's a pilot line that they've been operating for several years that does grow in place graphene on sapphire. And you can see our kind of workflow on the bottom there. And like I said, we can't grow in place on top of a CMOS chip, but we can grow in place on sapphire and then put things on top of that. Mm-hmm. In addition to the pilot line, there's a foundry that's opened last year that does more high volume manufacturing. And right now, Paragraph makes Hall sensors and biosensors, which again are not, in terms of electronics, super they don't have really high requirements on performance, but it allows us to find some niches and show that we can be commercially relevant and directly compete against conventional electronics, which I think is the key, right? Not competing in theory or in terms of what we can do in a publication, but actually competing in the marketplace. So I came to Paragraph because they acquired my company last year. So I'm in the San Diego office. So, hey, John, did you have something? I see you there. John knows Paragraph a little bit. Okay. It's my personal roadmap for integration of 2D materials into electronics. I think that, in the short term, I tried to put years on this. I think that we need to focus on growth of TMDs and other MXenes. I think that we've done a lot with graphene, but graphene shouldn't be the focus of what we do going forward. And we need to work towards, in the medium term, heterostructures grown in place, meaning instead of looking at oxide deposition via plasma or ALD, we're actually growing in place other graphene-like materials such as hexagonal boron nitride on top of the TMDs and other things. I think that for dielectrics, we do need different deposition techniques like I talked about, and we need to have some goals, and this is where the subtle difference comes in from the mapped roadmap. We need to have some goals on yield and manufacturability. I would love us to kind of put in place in future roadmaps, crunchy numbers, right? Goals for yield, on goals for wafer size. Like, let's show demonstration that we can do 6-inch, 8-inch wafers with yield of 50%, 70%, 80%, right? Like, where how can we get to those points? We need to look at some new contact metals, and then again focus on how do we improve yield and manufacturability with those. And then we need some new switch architectures. So not all of these types of materials are going to fit easily into this kind of MOSFET style architecture. Sometimes we may be better suited if we used a hot electron transistor, or two-dimensional base gated transistor, or some sort of FEFET, negative capacitance kind of transistor. And then we need to figure out how do we make complete architectures using those types of transistors. And so these are things that are floating around in a lot of kind of good academic work right now, but how do we actually use them in a practical point of view? I think we should focus on packaging and wafer bonding as much as possible at as early stage in research as possible. Yeah. The worst thing that can happen is you figure something out and then you discover that a particular design can't actually be packaged because you've screwed up your surface, your heat sensitivity. You need to kind of figure something else out, and we need to start moving away from just wire bond and glob top, and we need to be able to say that we can do some of the types of packaging that we talked about through the mapped process. Like, how do we integrate our chips with those types of packaging? I don't know that I've ever seen anyone do that, and that's not going to be super easy, because we want to get to the point where we have integrable chiplets that fit with the vision that we've established for heterogeneous integration. And so we need to start mapping out how do we get nanomaterials containing chips into that that mindset, that capability. And then the devices that everyone's working on. So right now it's a lot of sensors and filters. I think that in the 10-year range, I would hope that we're able to have some commercial push into amplifiers and extreme environment chips, because I think in 15 years we're going to want to see digital chips, and it might start off as just low power digital chips, but at some point we're going to want to get into that. I think that the thing we want to be careful of is it's really easy to get caught up into the hero devices and the excitement of kind of demonstrating something new. And I'd like to see us encourage some industry work or closer work of academics with industry. So these things I've highlighted in yellow are the things that I think really need to be focus of academic work right now. But then the flip side of that is, we don't want to develop something in an academic clean room and have to completely redevelop the whole process for several years in a commercial clean room. You want to be able to kind of move things along a bit faster. So as much as possible, if we can combine efforts, that would be great. One of the things I learned over doing nanomaterials for as long as I have is that it's really easy to underestimate the difficulty in going from an academic work to industry work. And so, again, one of the things I mentioned in the beginning is we are starting to see a commercial nanoelectronics community. I mean, it's like Ramon, myself, and a handful of other people, but there's some of us who are out there who are really, now we've got this kind of yield and practicality story going in our head, and we're not all, I would say, exactly on the same page. There's still a lot of debates going on, but if we can cultivate that culture within the electronics community and eventually, absorb so that that's not nanoelectronics, it's just electronics. But we need to, as we're looking at these new materials, focus on scale and economy and performance. And these bullet points here, I imagine if I just talked about them generally for electronics, most people here would agree, yeah, these are the things we need to work on. But we really need to emphasize this with the nanoelectronics community, not backslide into, hey, I published a paper and I demonstrated this device happened, once or twice. It needs to be like, okay, did you teach someone new how to make this? Did you set up a production line at another facility? Do you really understand your supply chain? Because those are going to be the differences between, just doing something that looks promising but doesn't ultimately result in a, contribution to the industry, and something that really can help the industry do the kinds of things that we need to do. So I've talked a lot, and those are the ends of my slides. So any thoughts? I'm sure Roman's got some ideas. Yeah.
Hey, Brett, I really like the last slide where you highlighted some of the areas that need work. I think in that slide in particular, right, the top line, growth, right, even the transition metal dichalcogenides, which kind of are, a little bit further along and are of interest to industries. You showed industries already integrating them in very complex devices. There's a gap that exists in the quality of the materials that can be grown at high temperature versus low temperature. And so I think, to add even a little bit more, focus to that row, I would say, is there a way to get the quality of those low temperature growths, which open more, practical integration paths? Is there a way to close that gap, bring up the quality of those low temperature growths?
Yeah.
Thank you very much, Brett. It is a great talk, and actually, this kind of talks is very useful for younger generation of fresh graduates who look around and thinking and having ideas, ambitions. So I'm glad that we have recording of this talk, and we'll put it on our open access website. It is great. So I would like to start the discussion, and Jim Ank is the first.
Very good. Thank you. Thank you, Brett. And I'm glad you still have this slide on. I'm curious where you see R&D investments in the CHIPS program as filling in this gap, this bridge between academic research and practice in industry, and in particular, you shared a lot of background and experience on the differences between academic research, where the focus may be on paper publication, and actually getting new technologies into practice. And I can see opportunities where there are investments in the CHIPS R&D program for Natcast or advanced packaging that may be kind of this middle ground, that you don't have to necessarily get these 2D nanomaterials directly into a fab, a production fab, but they have an intermediate target for proof of concept. And if there is this intermediate target, where do you see the best opportunities for targeting this intermediate step?
I mean, I think you laid it out really well there, right? Trying to get something that's maybe not made in the fab but goes through packaging sounds great. And part of the, and again, to throw it to Ramon, one of the reasons that I asked for Ramon to come was I really like the way the Jump 2.0 program works, where you've got academics working on things, and then you've got industry people doing regular reviews and regular conversations. And I think if we can encourage that kind of approach, even more, I think that would be helpful.
All right. So are the things that are highlighted here still the places that you would want to target then for this kind of intermediate step?
Yes, right. Yeah. Can you make a device using a new contact metal, using a new deposition approach, and can it go all the way through packaging and show performance relative to some existing conventional electronics? We can understand, in reality, how the whole process is working.
Great. Thank you.
Thank you, Jim. So I'm next. I have 3 questions, but since we have already a line, I ask one, or make a comment perhaps, or question. So you said that packaging is everything for success of say, 2-dimensional devices. But I would argue that mapped offers maybe best opportunity for this, because having TMD LEDs, now everything is LEDs, chip LEDs, whatever. So TMD, I call it TMD LEDs. So if you have TMD LEDs that can be integrated within advanced packaging platform, say by analog devices, for example, and Dave Robertson's next in the line, it is just, I would say, direct and clear path forward. Or
yeah, I would agree, right? So if I really like the heterogeneous integration concept and the chiplet concept for integration of 2D materials, but I don't know everything that's happening in the 2D field, but I haven't seen anyone actually do that yet. So I'd love to see someone actually do it.
Be the first. You already, Paragraph already making these devices, right? Let's say sensors, biosensors.
I've definitely pitched that, yes. And actually, so John Goodenough and I John put in a proposal to the UK government to do this, right? So, which I was very happy to support.
Okay, very good. Dave Robertson.
Well, and I think I want to compliment you, Brett. I think, Victor, we can, and to pick up a theme that Jim talked about, this presentation should be earmarked as a very interesting case study in crossing the valley of death, right? So between academia and commercial production. And so when we talk about NSTC or NatCast that's supposed to do this, you put out some very interesting observations, and we could probably even take them into some first principles. One of the things this table highlights, which is, trying to leap right into VLSI may be a little tricky. So the idea of, hey, can I use the technology to make sensors initially? And that's some of what ADI is doing. And then after that, can I make some niche amplifiers? And then, so I think the progression there. But I think the other thing, and Jim Ong, and I know Jim Weezer's on the phone, and he and I are wrestling with trying to scope out what an analog mixed signal initiatives might need to be for NatCast. The idea that you haven't exposed even half the problem until you've actually put the damn thing in a package. So when we could talk about cyber shuttles, we can talk about fab runs and things like that, but as we budget for NatCast activities and really think about where the money should go and how we create the balance, we need to kind of keep at least half the budget for putting it in a package and putting that package on a board and things like that. Because again, Victor, we say, oh, chiplets solve the problem. But as Brett already said, you can't touch this stuff to pick and place it because it scratches too easily, right? So there's this, but I got my PhD signed off because I made the device work, because I got 3 measurements done before anybody had to breathe on it, and I was fine. But as soon as I try to bring it into a factory, all hell breaks loose. So I think so, back to your point, Jim, about what should NSTC and NatCast do? Again, the idea of full flow, not just cyber shuttles, but we'll put this onto prototype platforms. We'll put it in a package. We'll spend some money there. We'll kind of work this back and forth with NAPMP. I think this is a wonderful case study and examination. Again, the solutions aren't all provided for us, but you kind of laid out. Don't forget to ask these questions. So I think this is great. Thank you very much for this.
Thanks.
Thank you, Dave. The next is Clifford King.
Yep. Hi. I just wanted to give the group a little data point that somebody brought up the CHIPS Act funding for this. As part of the Northeast Microelectronics Coalition, we actually strongly were trying to propose some 2D material work. The feedback we got was, this is too researchy. It's not a high enough technology readiness level for us to be able to fund. So just that's what people are thinking out there, at least as part of the Microelectronics Commons. But maybe we can influence the NSTC work and NatCast, as Dave was just saying. But I think it's going to take some voices out there saying that, yeah, no, this work is a little further along and does and is ready to do more scaling and actually put it in a device. But that wasn't the case for ME Commons so far. So,
which may mean that we've got some more messaging to do in the 2.0 version of the MAPT roadmap, right? To say, yeah, this isn't ready to replace the massive Intel processors, and again, back in the AMS corner in particular, this is ready to go commercial.
May I interject? And Ramesh Chauhan put something in chat, a question which kind of very relevant to current discussions. Ramesh, is you still online? Could you formulate this? So the question is in chat, and in short, it says that focusing on sensors for TMD-LEDs may be the right thing to do, because there is expected big growth of sensors of all kinds and integrated circuits. So maybe at this point we don't need to target, say, high volume digital applications and use this opportunity to grow with integrated sensors. I think it is what Ramesh asked. Ramesh, it is your. Did I correctly interpret your question? Oh, Ramesh is apparently.
Yeah, I think Dave made that point as well from his perspective. Yeah.
Yeah. Okay. Good.
Well, I didn't make the point. I just read the table here, which I think again, I think Brett did a great job with this table. Yeah. Again, consistent with that MAPT 5-year, 10-year, 15-year Horizon 3. That's why we have roadmaps, right? And says this is where we cross the chasm first with the smaller devices, where if you can make a handful of devices yield, you can start to build your manufacturing experience.
Yeah,
that's part of why I think biosensors and Hall sensors and things like that are good. There's going to be markets there, and there's going to be things that we can do that might actually outperform conventional materials, and that's an impact that can be made now.
And you can be commercial with 50% yield on a 6-inch wafer and still be in some business, whereas there's a lot of other parts of the semiconductor industry where you don't even have table stakes yet. But I think that's right.
Right.
Yeah. Okay, John, good enough.
Okay, yeah, so great. Thanks, Brett. Good presentation. And yes, I would love to get that proposal funded somewhere. I don't care where. It's good. Actually, I love this. So first thing, I love this slide. I would love to see the same slide for the quantum class, the quantum world devices as well. That's so Victor, that's kind of a note for you, because I think that in fact that sort of the methodology and approach, I think would be also very highly appropriate for some of the, you know, emerging, let's call it differentiated photonics material stacks propositions for quantum. And yeah, coming back, I think that they're all just, to me, subcategories of AMS. It's just AMS on a different material stack generally. So that's very good. I had one technical question. I wanted to just push on the note that was made about the high temperature versus low temperature and what the rationale for that was, because you were partly kind of going, actually, I'm going for chiplets into HI. So to some extent, I don't care about the manufacturing process for the chiplet or die in my novel weird material, because I'm going to HI it. And then back to what Jim was saying, it's all about the packaging in the HI context then. And I was just left with that thing at the back of my mind. Is there some temperature weirdness in the manufacture of this class of 2D materials that's not going to prevent me from doing hybrid heterogeneous integration?
Well, I think that the chiplet approach and doing high temperature growth should work just fine, and that with proper encapsulation, you don't have the kinds of issues that I was talking about. I mean, I'm telling you all the problems that I see. It shouldn't be shocking that those are the things I work on, right? Being able to do pick and place, being able to do integration and do packaging and all of that kind of stuff. And from my point of view, and definitely a paragraph, high temperature growth is what we do, and there's no problem with it. But there's other points of view in the field which you know are that you should push on low temperature growth so that you can have more complex structures underneath. And just saw Ramon unmute. He might be able to talk to that a bit.
Yeah, I think my comments on the gap between the quality of high temperature and low temperature growth were aimed at Brett's first slide, where he showed some IEDM results, or I think it's like a recent paper from industry that's showing a need for 2D materials in very advanced nodes where the gate length is below 10 nanometers and the thickness of the channel is below 5 nanometers. Then they begin to look interesting in comparison to your standard silicon channel.
Okay, so it's low temperature for back end of line growth on inverted commas future standard CMOS.
Yeah, it's basically opening more integration, pathways.
Got it.
3D homogeneous integration.
Yeah.
Okay, thank you, Sadas.
Yes, can you hear me?
Yes, we can.
Okay, so you have captured in your table contact resistance, which is an issue with 2D materials, as you know. So just building upon that, integrability is a key factor because you have to integrate the 2D materials with the CMOS flow. I didn't see you mention that here. Is it because you think it's not a problem yet, or is it a solved problem?
No, I definitely think integrability is important, and maybe I don't call out integration explicitly here on the contact materials, but definitely I agree with you, that's something that needs to be thought of. We can't come up with a contact scheme that can't be scaled, that can't be integrated. It's got to be something that we can use. So, that's part of the overall idea of how I think we should focus in our field.
All right, because if it's a front end versus back end, if you're getting as part of some 3D stack architectures, then you have two different integration schemes, and this typically ends up being the gating item if you want to integrate it into CMOS. So I thought I'll just bring it up.